5 weeks. That's all SpaceX needed to build what used to take 3 months. Booster 19, the second version 3 Super Heavy, just rolled into final assembly at breakneck speed while NASA got its youngest administrator ever in Jared Isaacman. But here's what nobody saw coming. The modifications at Massey's test stand reveal something bigger than just faster production. What if this speed isn't about recovering from the Booster 18 explosion? What if version 3 was designed from day one to change everything we know about rocket manufacturing? The answer lies in what happened on November 21st at 4 a.m. Booster 18 exploded during testing, a complete loss. Most companies would need months to recover from such a setback, analyzing failure modes, redesigning components, rebuilding confidence. SpaceX had Booster 19 segments rolling into Mega Bay 1 by December 18th, 27 days later. This isn't just impressive response time. This proves version 3 represents something fundamentally different in rocket manufacturing. Booster 17 required 3 full months of stacking time without delays. That was the previous record, and SpaceX celebrated it. Now, 5 weeks total for the largest rocket booster ever constructed. But speed alone doesn't tell the complete story. While everyone focuses on Booster 19's record assembly, Ship 39 sits ready for cryo testing and static fire. Completely prepared. Yet SpaceX isn't moving it to the test stand. The reason reveals everything about what version 3 is really designed to accomplish. Our aerial survey with Redline helicopter tours captured something critical. A new structure attached to the Massey static fire gantry. Simple girder work positioned precisely adjacent to the flame trench, designed to reach something specific on a mounted Starship. Not the quick disconnect port that's already covered. This reaches the front of the vehicle, where version 3 has its orbital refueling ports. This is what everyone's missing. Version 3 isn't just another iteration. SpaceX needs this generation to validate everything. Payload deployment systems, long-duration orbital coast to measure fuel boil-off, the first real propellant transfer between ships, Starlink 5-3 satellite deployment, and the new heat shield configuration. All before committing to the HLS lunar lander variant that NASA's Artemis program depends on. All in 2026. Those refueling ports aren't simple docking mechanisms. They're the interface through which cryogenic methane and oxygen will flow between tanker ships and destination vehicles at orbital velocities. The connections must handle extreme temperature differentials, maintain perfect seals in vacuum, and operate reliably after months in space. You can't validate that without proper ground infrastructure, which explains the test stand modification and why Ship 39 waits. The testing protocol shows SpaceX's confidence in this design. Test Tank B-18.1 just endured a 15-hour continuous cryo test at Can Crusher 2.0. 15 hours. No flight booster experiences that duration of stress. This is reusability validation at the component level, finding failure points before committing the design to production. The data from these torture tests feeds directly into the flight hardware being assembled right now. My timeline analysis based on these milestones. Ship 39 cryo testing in late December. Booster 19 cryo testing January 4th to 10th. Booster 19 static fire January 18th to 24th. Ship 39 static fire end of January. And Flight 12 launching February 1st to 7th. Each validation builds confidence in the architecture that will eventually refuel ships in orbit and land humans on the moon. Then December 17th changed the entire landscape. The Senate confirmed Jared Isaacman as NASA's 15th administrator in a 67-30 bipartisan vote. At 42, he's the youngest administrator in agency history. But age isn't what makes this unprecedented. Every previous NASA chief came from traditional paths: academia, government service, established aerospace careers. Scientists and engineers who understood committee structures and appropriations processes. Isaac Mann built a payment processing empire from his parents' basement at 16. Shift 4 now handles transactions for one-third of American restaurants and hotels. He used that success to accumulate over 7,000 flight hours, set a world circumnavigation record, then commanded Inspiration 4, the first all-civilian orbital mission that raised $240 million for St. Jude Children's Research Hospital. What Polaris Dawn revealed about his capabilities changed the conversation entirely. The mission reached 1,400 kilometers altitude, farther than any human since Apollo 17. Then Isaac Mann opened the hatch and conducted the first private spacewalk, testing SpaceX's EVA suit while traveling at 27,000 kilometers per hour. He didn't just fund these missions. He commanded them, trained for them, and risked his life to advance human spaceflight. Now he inherits an agency racing China back to the moon, while preparing the most ambitious crewed mission since Apollo under crushing budget pressure. The challenge runs deeper than technical execution. NASA operates multiple centers across the country, each with congressional representation protecting local jobs. The agency awards contracts through procurement processes that favor established players over innovation. The entire Artemis architecture depends on coordination between legacy contractors and new commercial partners who operate under completely different paradigms. This is where Isaac Mann's background becomes critical. He understands rapid iteration, acceptable risk tolerance, and commercial efficiency. But can he navigate federal bureaucracy? Can he unite disparate stakeholders around common goals while pushing for transformation NASA desperately needs? The answer matters because the tools at his disposal are evolving faster than the agency itself. Consider Rocket Lab's Neutron approaching first launch. Peter Beck recognized that you don't break SpaceX's 85% control of global launch mass by copying Falcon 9. Where Falcon 9 stands 70 meters tall with 3.7-meter diameter, constrained by truck transport, Neutron is 42.8 meters tall with 7-meter diameter. Short, stubby, and uniquely proportioned for a specific reason. That unconventional umbrella shape enhances aerodynamic stability and glide performance during booster return. SpaceX recognized this principle when Super Heavy version 3 moved to asymmetrical chine placement. Blue Origin built large fixed fins onto New Glenn from inception. Neutron optimizes the entire vehicle geometry around atmospheric return rather than treating it as an afterthought, maximizing downrange capability without wasting propellant. The Hungry Hippo fairing takes this philosophy further. Traditional fairings protect cargo, split, and discard. Neutron's fairing opens, releases the second stage from inside the first stage, then closes again. When the booster lands, the fairing returns with it as an integrated unit. This eliminates separate recovery operations, enables rapid turnaround, and allows the second stage to be exceptionally lightweight since it never experiences direct atmospheric forces. Rocket Lab's 90-ton automated fiber placement machine lays carbon composite at 100 meters per minute. What takes human crews weeks to build by hand, this system produces in 24 hours. The weight savings compared to aluminum or steel are substantial, and the manufacturing speed enables the kind of iteration SpaceX demonstrated with Booster 19. This is the industry Isaac Mann now leads from NASA's perspective. Not the world of cost-plus contracts and decade-long development cycles, but an ecosystem transforming itself in real time. where rocket boosters assemble in 5 weeks, where private citizens conduct spacewalks, where manufacturing robots change the economics of orbital access. NASA must either lead this transformation or become irrelevant to it. So let's connect what we're really witnessing here. 5 weeks to build Booster 19 isn't just SpaceX recovering from a setback. It's proof that version 3 was engineered from the ground up for manufacturing speed that seemed impossible 2 years ago. The modifications at Massey's test stand aren't delays. They're NASA's future orbital refueling capability being validated on Earth before risking it in space. And Isaac Mann taking the helm at NASA right now, with his Polaris Dawn spacewalk experience fresh and his commercial mindset intact, puts someone who actually understands this new industry pace in position to align America's space agency with reality. February 2026 brings Flight 12 and the first real-world test of everything version 3 promises. Neutron's inaugural launch will prove whether Rocket Lab's unconventional approach can compete with Falcon 9's dominance. New Glenn will continue demonstrating that glide capability matters for reusability economics. And somewhere in all of this, NASA must figure out how to lead an industry that's already moving faster than government procurement can track. The paradigm shift isn't coming. It's here. The question is, who adapts fast enough to shape what comes next? What's your prediction for Flight 12? Drop it in the comments. If this analysis brought you value, hit that like button and subscribe to New Space Review so you don't miss what happens when these systems actually fly. Share this with anyone who still thinks space moves slowly, because in 2026, slow gets left behind. Thanks for watching, and I'll see you in the next one.